Okay, so this is a question to do with projectile motion, and in this example we have the added complication that we don't just have gravity acting on the projectile, but we also have this drag force. So this drag, which is defined as minus kV, so it's only linearly proportional, to simplify it a little, linearly proportional to the velocity. But of course this drag force, the component of this drag force is always going to oppose the motion, but that motion is going to change during the trajectory of the projectile. So at certain stages, if your velocity is in that direction, then of course your drag will be in that direction. But of course, if your velocity changes subsequently to be in that direction, then your drag is also going to change. So we need to take into account of a change in direction of drag, and the way we do that is by using vectors. So you have the aerodynamic drag, which is minus kV, where v is a vector, and you break that up to be vx and vy in the I and the j unit vector directions. If you combine that with the gravity, the acceleration due to gravity, which is all the time in the down direction, then so you've all the time got, put an arrow there for that, all the time you've got the gravity going down, then the total acceleration you experience is represented here. So this is a vector sum, and so in the I direction you have minus k times vx, and in the j direction you have the combination. You have minus k times vy, but also you have the g component as well, and because it's in brackets with the minus before it, then this comes out to be positive. So if you want to find the x and y components of velocity and displacement as a function of time, you're going to have to integrate this expression in each coordinate direction, and you're going to have to integrate it twice. And that's all the question boils down to. So you need to integrate each component separately, and this is what I want you to start thinking about. What does the question translate to? And this is the key to the whole question. So we write down our vector, we have our drag vector, so just the same as what has been defined before, and we start with the x component. So we have ax is equal to dvx dt is equal to minus k vx, and we rewrite this as follows: between vx naught, or the initial velocity, to vx, and it's the integral of 1 over vx, which is going to be the natural log of vx between vx and vx naught. On the right hand side, k is a constant, so you're just left with minus k times t between t and t naught, which is of course just minus kt. Because you have the limits subtracted one from the other, you're left with a fraction, which you can then obtain on its own by taking the exponential of each side. So here you take the exponential of log to get the fraction on its own, and here you take the exponential of minus kt to get e to the minus kt. And finally, to get the expression for velocity, you just move over vx naught to the right hand side, and you're left with this expression here. So you've completed the first part of that question for the x component. Now you have, if you want to get the displacement, you have to integrate again. So slightly more complicated. To integrate again, you take the expression for velocity that you've defined, and this is equal to dx dt. So you have then the integral of dx on its own and v times dt, and because your v is a function of time, that's going to work. So the only functional variable there is time. So on the left hand side the integral is just x, on the right hand side you're going to have to integrate this function, and fortunately the initial projectile angle is constant, so that comes out of the brackets. So you have v naught cos theta as the initial component of velocity in the x direction, and inside the brackets you have the exponential of minus kt, which when you take the integral of that, you're left with 1 over minus k between t and 0. If you multiply out those, if you substitute in those limits, you get the following here. And you can simplify that further as follows. So you get 1 minus the exponential of minus kt times by this, which is a constant. Now at this point I make a note that's going to help us a bit later, just summarizing the integral that we've just done. When you want to integrate something of this form, the result is going to be this. And the reason for making this point will become clearer as we go to the y component. So just generically said that the integral of this can be written as a times the exponent to the minus kt becomes this form here. So this is the thing we're going to take to the next section. Okay, so moving on to the y component. So with the y component, it's exactly the same. You start out with ay is equal to dy dvy by dt. And this time the acceleration in the y direction has minus kvy, but it also has gravity. So we simplify slightly this expression so that we have vy on its own. So we divide through by k. So we have g over k and we have vy. And the reason we do that will become clear in a moment. So that allows us to divide both sides by this, and we're left with the integral in terms of vy on this side and an integral for time on this side. So on the right hand side it's simple. The integral of a constant becomes a constant times the variable time. And on the left hand side we're left with this. So the integral of this denominator is simply the natural logarithm times the denominator between the limits vy and vy naught. Again, because one is subtracted from the other, you're left with the natural log of this fraction, which if you take the exponent of this, you have just the fraction on its own, and you have e to the minus kt, and very similar to the way that you had in on the x direction. So, yeah, let me just get that on the page. So the expression for vy changing in time is defined here and then simplified here. So vy is equal to vy naught plus g over k times e to the minus kt minus g over k. And you can also explicitly put the angle in by denoting the y component of the initial velocity as v naught sine theta. Now, to get the displacement in y, you have to integrate again. So you have this expression, and you have y is equal to this expression times dt. So you have to integrate this in time. Now this is where the note we made in earlier in this question comes back to help us. So we said that the integral of this constant, or this expression a, times e to the minus kt, the result is a over k times brackets 1 minus e to the power minus kt. Now we can use that exact same form here. For a, we can put everything in the brackets here. And simply we can say that the integral of this is then a, which is this term, times 1 over k times 1 minus e to the minus kt. And all that's left is to integrate this term, which, because that's a constant, it just gains t. And the final form for the displacement as a function of time in the y direction is obtained here. Now, the last bit of the question is quite a nice example of why this analysis would be useful. It's asking you to find out the terminal velocity of the projectile. Now, of course, the terminal velocity will happen as time goes to infinity in this model, so we can look at our expression for the x component of the velocity and the y component of the velocity and see what they're going to predict for infinite time. Now, because the minus exponent looks a little bit like this, then as you go to infinite time, this is going to go to 0. So in the x direction, your projectile is eventually going to have a 0 velocity. Whereas in the y direction, again, this first term has a minus exponential, so that's going to go to 0, but you're left with this term. And crucially, this is the terminal velocity. The terminal velocity is then minus g divided by the constant k. And it makes sense that if you fire this projectile, I'll just sketch it again here. You've got your tank, you've got your projectile. Eventually, if you leave it long enough, it's going to, and we're going outside the tank, but you get the idea, it's eventually going to become vertically downwards. And what we're saying is that the terminal velocity is going to be minus gk. And that's it.